Today I would like to study conjugate heat transfer in OpenFOAM, where we process geometry and create mesh in Salome. Here in this case, we have a plate fin heat sink which is connected to a heater and which is being cooled by incoming air. The objective of this tutorial is to explain the whole workflow, starting from creating the regions for each solid region and for fluid, making boundaries, creating mesh in Salome, moving this mesh to OpenFOAM, setting up a case in OpenFOAM, and doing some post-processing. There are many things that we can compute from such a simulation, but here, as an example, I want to compute, for example, the thermal resistance from ambient to heater junction, and that can be computed if we have the temperature at the interface between heater and the fins. And once we have that, we can compute the junction temperature that can be used to compute the overall thermal resistance. And this can be then compared, for example, with an experimental uh, configuration as well. So let's start. Here in Salome, I have geometry of fins as a separate part, as well as heater and the duct. First thing that we need to do is to define the fluid region in the duct. So we can select, for example, the duct, and we can use this cut tool, and for example we can name it fluid, and then I can remove, for example, fins from it, and then we use apply and close. So now we have our fluid region. So if we can see it a little bit better. Okay, so now this fluid region does not contain the fins. Now the next step is to combine all these regions in a way that we can define separate regions for fluid, for heater, and for fins. And this can be done using partition tool. For example, we can, using control, we can select fins, heater, and fluid, and we can go here and select partition tool, and we can name it, for example, fluid, heater, fins, and we apply and close. So now we have one region that contains everything, but it will automatically make these partitions where one region is connected to the another region. Now we have defined regions. The next thing that we need to do is to define the boundaries, and we can do that using create group, and then we select faces, and for example here I want to put my inlet for fluid at minimum Z, so I can select that face, so I can put it as unit of fluid, apply. Similarly, I can set outlet patch for fluid, apply, and I can select walls for the fluid region as well. In that case, you need to press shift to do multiple selection, to activate multiple selection, and finally edit the 4 faces. So similar, now I need to also set the walls for heater, which are these faces, all of them. With shift I can select multiple faces and then I will add them here, apply. And the last thing is the base of fins, which is this face. I add it and apply and close. So we can see we have this for fins, heater wall, fluid wall, outlet and inlet. There is no need to define the faces which are shared between each region, because that can be done automatically inside OpenFOAM. So once our geometry is ready, we can, and we have our groups and faces defined, we can now start to make a mesh. In order to make a mesh, we will move to mesh module. Inside the mesh module, you can select all the regions and here create a new mesh, and we can select, for example, NetGen algorithm. We can put some parameters. For example, I want maximum size to be 20, minimum to be 1, and I can also set sizes based on the region. For example, on the heater region, I want a size of 2, as well as on fins, I want a size of 2. And that's it for meshing parameters. And what we need is just press compute mesh. So here is our mesh with about 207,000 volume elements. We can see a little bit in more detail by using clipping here and defining a relative clip. And now we can see the mesh here. We still need to add the regions to this mesh before we can export it. So we can go here and select create groups from geometry and select all the region and faces and apply and close. Now we can see individual regions as well. For example, we can see the heater as well as fins, but also, for example, different boundaries. So once we have our mesh, we can just go back here and export it as UNV file. I can find it later, so I have defined a new folder for that. So for example, I can put here fluid heated fins save. So now our mesh generation in Salome is complete. So our mesh is ready. Now we would like to export this mesh in OpenFOAM. But in order to convert this mesh in OpenFOAM, we need to set up a case first. For example, the easiest way is to copy a case, for example, in this case, from the tutorials of CHT multi-region form, and then modify it. So we can copy that from tutorials, heat transfer, and maybe you can use heated duct, and I need to name it plate fin heat exchanger. But before trying to modify all steps, we can quickly go ahead and test if our mesh is fine or not. So we can just run, and the name of the file which we have in the parent directory, so we can just run, and as we can see here, we have 3 cell zones and we have different patches that are defined as well, and there is no error message. However, this is still one mesh. In order to make mesh for each region separately, we need to run lit mesh regions, then all cell zones, and then we need to overwrite as well. So now we can launch Paraview or OpenFOAM, Parafoam. But before that, I want to make some file that I can read with Paraview, and we can quickly see if everything is fine with our mesh. So we can go here. So we can see that we have different color for different patches, but we can check it with the further detail by using extract block. For example, I just wanted to see, for example, the heater region, and I have it, and maybe just only the patches. So we have only 2 patches. One is heater to fins and other is walls of the heater. And similarly, we can see on the fin side we have good mesh as well, and we can also see different patches. So we have one for the base and one that is shade between heater and fins, and the one and on the top that is shade between fluid and fins. So this is a quick way to test our mesh. Now we have to set up our case correctly by modifying constant as well as setting correct boundary conditions and do other modifications. So I have this case here. So it is always good idea to change the script here so that we don't need to type everything. In our case, we don't need the block mesh or also snappyHexMesh, but we need conversion that we define here. So we can use that here. Similarly, we can add if we want to rescale our mesh. For example, in this case, I want to rescale, and it can be done using transform points, rescale, transform scale, and then we can give, for example, in X, Y, and Z the scaling factor. So this will scale something like this. So we can add that as well in our all run script, so it is easier to perform the next iteration. And then we need split mesh in order to separate each zone, and for now we do not want any of this step. So the next step is to modify or to adopt the tutorial to our needs. In the actual tutorial, we have on. So first thing that we need to change is the regions. So we have a heater and fins, and similarly we can rename, we can use the data from the case as well. For example, from the heater the data is already there, but for the metal we can copy this information inside the fins. Similarly we need to do, so let's start with setting thermophysical properties first. So we need for each region to set the correct thermophysical properties, and for the heater we need to set heat source as well. So if I go here, constant and heater, so for in the thermophysical properties we have a different material, and I have already this information, so I can use that. For example, from my data file, and similarly I have information for others that I can use in this case. For example, for fins, which is in this case is the same material, so actually we don't need to change that. And then for the fluid, in our case it is air, and I can use, for example, the data I have for air. In the fluid. So I'm using here a constant density, but we can also use perfect gas equation. In case of heater, we need to set a heat source, but this heat source is, we have an input of 56.64, but this is in watt, but we need here specific heat flux, which is watt per meter cube, and we have cube of 12.45 millimeters, and it turns out to be 2.9 ECM. So in case of fluid, we need to set turbulence properties, which are in this case laminar, and we don't need to specify the gravity. We have correct thermophysical properties for fins as well as for heater. We don't need this metal, so we can just remove it. And the next step, so we have now modified properties for each region, and now we need to set up the boundary conditions. But before, we just need to see what are our boundaries. So if I go here, and in the fluid regions, so we have 4 boundaries. For fins we have 3, and similarly for heater we have 2 boundaries. This is the shared boundary between heater and fins. So with this information we can start setting boundaries in, for example, heater first. So in our case, the input 1.9, we have this, we don't need this constraint, and now we have the names in case of, so wall was the heat, and we can set that here. For now we assume it is adiabatic, so there is no heat transfer, and instead of heater to metal we have heater to fins. So for P we don't need to do anything, we just need to remove this setting. and we can copy the same data from heater to fins as well, but now we need to change. So in this case we have base of fins, but here we have fins to heater. But we have another one that is fins to fluid. For P we are good, and now we can set boundary conditions for fluid region as well. So in T, here we can just, instead of titling each, we can just use this setting that will take into account all the boundary condition that has this phrase in it. We do not need this. And for inlet, the temperature side we have, and we have inlet on the fluid side, which is a fixed value, and outlet at the fluid side will remain same. And we also have walls, and in this case we can put fixed value of 0. So we can see the constant fluid polymesh boundary. We have inlet fluid, outlet, walls, and fluid to fins. So we can maybe use this directly here. Now we can set boundary conditions for velocity field. In our case here we have a different value along the positive z direction. We do not want this, and we need to rename it as inlet on the fluid side and outlet on the fluid side. And also actually this is for velocity, not for temperature. In case of temperature, we just need to define that it is like an insulated wall, so 0 gravity. Similarly, we can set P, we do not need this, and we can set here, this is the outlet for fluid. So basically that's it for our boundary conditions. We also want to modify our boundaries so that the wall is always defined as wall, and also in this case this is wall, and in case of heater as well everything else is over. So now we are done with our boundary conditions. Next we need to modify system finite volume schemes and finite volume solutions to set discretization for schemes for time and velocity and other quantities. So now we can update finite volume schemes and finite volume solution file for each of the regions. So if I go here to heater, for example, we want to study here a steady state condition. So the only thing that we need to change is this for the time scheme, and we will copy the same data to the fins as well. And in the fluid as well, we need to set it to steady state. So that's good. And the final thing that we need is to modify controlDict file, which is in system. I will remove this, which is not required, and so now in the controlDict we want to run a steady state simulation, so we can run for example for 3000 iterations, and this is basically we advance one iteration, and the right interval is set to 100, and we do not need these because we are in a steady state simulation. We do not want to control our time step. One thing that we need to add is some post processing that is done by using some functions. For example, I want to monitor the maximum temperature in each region, or if I want to compute volume average quantities. So this can be done. I have already these files with me. So for example, I have file to compute maximum in each region. So if I copy them, so I have to put them in the system directory, and I have to put the correct name. So for this, the region is fins, and also here we have heater. Similarly, for volume average, we need to define the region. Operation is volume average, and then we can specify the field, and we can do the same for heat. In order to include that, we can just use include form and the name of the file. So Salome heater T, basically this is one. Similarly, we have Salome fins T temp and volume average fin temperature and volume average heater temperature. In order to compute the average temperature at the interface of heater and fins is a little bit complicated. So I have already done that. So basically it's defined with the help of a type of post processing that is called surface field value, and in that case we need to define the region and the name of the batch that we want to compute area average of T. We are almost done with our controlDict file here. We have included post-processing functions, for example, to compute volume average temperatures and also average temperature at the interface of heater and fins. Before running, I just want to add for fluid, when we have a coarse mesh like this, it's always a good idea to use under relaxation factors in steady state simulations so that the solution does not diverge. We also need to set non-orthogonal correctors to more than one because our mesh is not perfectly orthogonal. And one more thing that we can add is in the fluid region, we might want to limit the temperature, especially in the first few iterations. So we can do that by using finite volume options and setting temperature limit, and normally this will be active only in the first few iterations. And we can have a look at our all run script. So we can just run it again. So the first step is to convert the mesh, then rescale it, and then split the mesh. So I will go ahead and do that as well. So if I do all run, it will only make the mesh and then transform and then split mesh. It will split the mesh based on region that we define. And now we can check the mesh as well. So up till now everything seems okay. So we can run in serial. So we see here, for example, we are getting the temperatures, volume average temperatures, average temperature at the interface, and also minimum maximum in the fluid region as well. So this seems to work. And also we can see the temperature in the fluid region seems to be in the range that we expect. It is a little bit slow, so we can just stop it and run it in parallel. So in order to run in parallel, we can set our decomposition here, not in the system, and I want to decompose in 8 domains using simple method with 4 partitions in x direction and 2 in z direction. And in my all run script now I will use this to decompose, and then this run parallel get application will run application that is mentioned here in parallel. So I can just go ahead, do all clean, and then I run again, and now we will decomposing and we are running in parallel. We can monitor the temperature as well, for example using foam monitor. In the heater region we have this volume average temperatures, so we see that initially there is an increase in temperature because of the heat source, and we can also monitor, for example, for fins, the volume average temperature using the same method. So we have, after each iteration, the update of temperature for the fins region, and in the same manner we can visualize update of the temperature for the heater region as well. So we see that the heater temperature is a little bit higher because of the heat source, and we can also monitor the temperature at the interface, which is interface temp, right? And we can use average temperature that we mentioned in our controlDict. So this is a good way to monitor the progress of solution as well. Once we do not see any appreciable change in the temperature, we can stop our simulation, and we can also have a look at the log file. And we can see the number of iterations are not that much, so the solution is converging, and the temperature in the fluid region seems reasonable, as well as the temperature in the heater and the solid region. So we can wait until we do not see a big change in this solution, and once we are happy with our solution, we can reconstruct the latest time and all regions, and now I can visualize the results with Paraview as well. So, and I will follow the same procedures. So I upload everything here. So if I go temperature in the last timestamp, but it's better to use extract block filter and see separately each region. So we have over the fins, so the temperature in the fins, we can change the color scheme to be a little bit more vivid. So, and also we can see the temperature distribution in the heater region as well, and here we can put T like this, and similarly we can do it for the fluid region. So in order to see it more clearly, I can use clip, and so if I apply, so now I have the clip result for the fluid region, and we can see a slight increase in the temperature of the fluid as it passes the fins. Meanwhile, we can see our solution is almost converged, so we can maybe update our results. So I can reconstruct again a little bit later time, and then I can go reload file, and here so basically this is it. This is how you can visualize this case and monitor as well. We can also use clip on other regions as well. So for example, I will go ahead and group this data set into one, and then I will use here another clip, and if I put here temperature, so for now I can neglect this region as well, and we can see the temperature distribution here. Or we can also go here and change the setting to 20 so that you can see more clearly the distribution of temperature in fins as well as in the heater region. After some iterations, we can see that there is no appreciable change in average temperature as well as interface temperatures, so we can reconstruct our latest time, and we can stop our simulation as well here, and in the Paraview we can update again, and now we can see again the temperature distribution. So this is what a steady state simulation for this case looks like, and we can do some quantitative analysis, for example by computing the thermal resistance, and then we can compare that with some experimental data as well, which is available in this case. So here we have steady state result for this simulation, and we can also compute, for example, the interface temperature from the simulation, and then compute the thermal resistance, and we can compare it with experimental data from the article. So basically we started here with this configuration to reach at this point, and we can visualize the result also here in Paraview.